Hey guys, welcome to the first video of my In a Nutshell series where I'll be breaking down every topic in A-level maths. Today's video is going to be on indices, where we'll take a look at the definition for indices, combining indices under multiplication and division, indices with different powers, including a power of 0, negative powers, as well as fractional powers, and then we'll finish up with handling algebra involving multiple variables. The last thing is that every section of this video is going to be timestamped so you can easily jump to a section if you don't want to watch the whole video. Hope you find this helpful.
First off, what are indices? Indices are numbers written in the form x to the n. We would call x the base and n the index, exponent, or power. Let's take an example of 2 to the power of 5. This would represent 5 2's all multiplied together. In general, x to the n would represent n x's all multiplied together. Next, let's look at how to combine indices under multiplication. As an example, we'll look at x squared times x cubed. If we break each part down using the definition, that would be 2 lots of x, then multiplied by 3 lots of x. Counting up all the x's, we have 2 plus 3 lots of x, meaning the combination would be x to the 5. We can now see the general rule for multiplying indices of the same base is to simply add the powers. Now let's look at how indices combine under division. Consider x to the 5 divided by x squared. Let's rewrite both parts using the definition like we did before. We can rewrite this division as a fraction. Now if we cancel 2 of the x's and count the ones remaining, we can see the answer would be x cubed. The general rule for division of indices with the same base works out to be subtracting the powers. Next, let's look at how to handle indices with nested powers. Consider the example x squared to the power of 3. We can again rewrite this using the definition for indices as 3 lots of x squared all multiplied together. If we count up all the x's, we see there are 3 lots of 2, meaning the answer is x to the 6. We can now understand that the general result for x to the n all to the power of m would be x to the n times m. Now let's think about indices with 0 for a power. Consider x to the power of 0. We could rewrite this as x to the power of 1 minus 1. Recalling the division rule, we could rewrite this as x to the 1 divided by x to the 1. Finally, we know that anything divided by itself is 1. This means that all indices with a power of 0, regardless of the base, are equal to 1. Next, we're going to look at indices with negative powers. Consider the example x to the power of minus 2. If we recall the rule for division of indices, we could rewrite this as x squared divided by x to the 4. We could rewrite this again as a fraction. Cancelling 2 x's, we are left with 1 over x squared, which we would call the reciprocal of x squared. In general, indices with negative powers would correspond to the reciprocal of the corresponding positive power. Now let's look at indices with fractional powers. Consider x to the half times x to the half. Using the multiplication rule, we know this would be x to the 1. To help us understand what's going on here, let's think about the case where x equals 4. The red equation says something times itself equals 4. We know this simply as the square root of 4. Extending this logic, we can see any indice with a power of a half is just the square root of the base. Now let's consider 3 lots of x to the power of a third multiplied together. Again, using the multiplication rule, we now know this would be the same as x to the 1. Now we have 3 lots of the same thing multiplied together to give x to the 1. So x to the power of a third must correspond to the cube root of x. Generalizing this to x to the 1 over n gives the nth root of x. We still need to deal with fractional powers where the numerator isn't 1. Consider x to the m divided by n. We could think of this two ways. First, as x to the power of m times 1 over n. Using what we learned in the previous section and the nested powers rule together, this is the same as the nth root of x to the m. Alternatively, we could write this as x to the power of 1 over n times m. Again, using the nested powers rule with what we learned in the last section, this is the same as the nth root of x all to the power of m. In summary, x to the power of m divided by n can be written in two different ways that are actually the same. Last up, we need to look at algebra that involves more than one variable. If two variables, or a variable and a number, are multiplied together, we notate that by writing them side by side. If we want to collect terms involving multiple variables, we can only do so if the powers on each of the variables are the same. For example, 3x squared y cubed and 2x cubed y cubed cannot be collected as the powers of x in this case are not the same. However, we could add 3x squared y cubed and 2x squared y cubed to give 5x squared y cubed. So to reiterate, we can only collect terms involving multiple variables if each of the variables have the same power. Lastly, we need to be able to handle nested powers involving multiple variables. Let's consider x squared y cubed all to the power of 3. Let's rewrite this using the definition for indices. Now we can see there are 3 lots of x squared and 3 lots of y cubed. Using the multiplication rule, we can see this would come to x to the power of 6, y to the power of 9. So in general, when we have nested powers involving multiple variables, we multiply the outer power by the powers on each variable.
So that's the end of the video, guys. Hope you found this helpful. Here's a little summary of everything we looked at today. If you did find the video helpful, please consider dropping a like. That really helps me out a lot. And if you'd like to be notified when I release more videos, you can subscribe to the channel. Thanks, and I'll see you in the next one.